No, they're different identities. Can I, real quick? Oh, you know what? I have a copy right here.
I have 2 copies.
You do?
Yeah.
I know I have one though.
This is from Cal 1.
Oh, well, I need the whole thing. Hold on. It's all right, I got it.
It's stapled.
I got it. Okay, so I've been asked, are all the hyperbolic identities on here? And they are somewhere. Is it 5? No, reference page 4. Reference page 4, at the bottom are the hyperbolic functions. Not their derivatives, but the functions. Identities, no. I don't see identities here. But you're not going to need them. I mean, okay, it's not that big of a deal. But you do need to know their derivatives. So on reference page 5, at the very bottom, inverse hyperbolic functions, those are all the derivatives for the 6, the 6 inverse hyperbolic trig functions. All right. Let's see where we are here. Hanging wire catenary. All right, there's one last thing, and I have time. We don't have enough time to start the next section. But there is one thing I do want to show you that is, well, I like to show this because it's usually a type of algebra thing that most students have never done before, or if they've seen it, I don't know. It's weird, but it's cool. So I want you to see it. We defined the hyperbolic sine function, right? We define it to be 1/2 e to the x minus e to the negative x, right? That is the definition of the hyperbolic sine function. And then I told you that there are inverses of those functions, right? I told you that they exist, but I didn't go into any more detail. And then I said each of those inverses has a derivative. I would like to back up and go up to the inverse of that function and look at the definition of what it is. The inverse of the hyperbolic sine function is the natural log of this thing, right? It's weird. I want to prove why that's true. It's a disconnected idea from everything we're doing in here as far as derivatives and all that. But again, this is more for just an algebra thing. Yes?
So is it because of the fact that like exponentials and logarithms are inverses?
It has something to do with that, exactly. It seems to make sense that there should be a log here if that has e in it, right? Has e. All right, so I'm going to try and prove this to you, okay? I'm going to try and prove that that's true. So to do that, I need to go back and I need to see if you remember how we can find the inverse of a function. So I'm going to do a simple example first. Go back to college algebra and take something like this and find the inverse of it. Does anyone remember how to do this? Yeah, okay, so a lot of you know. What you do first, you replace f of x with y. Okay, you replace f of x with y, and now you switch x and y. Everywhere you see a y, put x. Everywhere you see x, put y. So I put x here, 2y plus 1, and then what do? Solve for y. So get y by itself. So you subtract 1 on both sides, divide both sides by 2. We solve for y. Once you solve for y, that's your inverse. So the inverse function is x minus 1 over 2. Let's just check that this works. Okay, let's just check. And when I say check, I'm going to check it for one value. If it works, I'll be happy. So let's take a value and let's plug it into that one. So let's plug in 5 into that function. What happens if I plug in 5 into that? You get 11? Okay. Now, if I take 11 and plug it into the inverse, I should get what? 5. Okay, so plug 11 in there. What do you get? 5. Okay, check. All right, it worked for one value, so yeah, I'm kind of happy about it. I'd have to check every value, which is impossible. So what we do to check it for sure is we do composition. We plug this into that, and we should get x when we do that. We plug this into this, we get x, then it works. All right, that's the method, right? Replace f of x with y, switch x and y, solve for y, you're done. I'd like to do that on that. So let's start out with The function itself. The function we're working with here is the 1/2 e to the x minus e to the negative x, right? That's the original function. That's the hyperbolic sine function. I'm going to try and find its inverse. So first, I'll replace the f of x with y. That's okay? Replace all x's with y's, all y's with x's. X equals 1/2 e to the y minus e to the negative y. There.
So that's where the natural log comes in.
Yes. Well, we know there's going to be a log, right? It's just when, okay? So now the goal is to solve for y, right? Solve for y. Multiply by 2. Let's do that first. I like that. Let's multiply by 2 first. And let me see how much time I have here. I'm willing to let you have 5 minutes to see if anybody can figure out how to solve for y. I mean, you can work together, talk. In my years, no one's ever been able to do it. Okay? Unless they've seen it before. I'm not saying it's impossible, but I have yet to ever have a class be able to solve for y correctly. They get y, but it's wrong. They do something wrong. So I'm only giving you 5 minutes, though. See if you can at least come up with an attack, like a plan, to solve for y. I'll be back. Any progress? Anyone want to kind of throw an idea out there to me, or?
Do you take the derivative, find the inverse, and then take the antiderivative?
I don't think that'll work, because
So
Yeah.
you take the natural log of both
if you take derivative with respect to what? X? And then integrate?
Like, yeah, I guess so.
And then find the, no, because there's nothing that says that that has to be true. That,
Well, it doesn't always have to be true, but it's
no,
true in this case.
yeah, no, the inverse of the, if you take a function and you look at its derivative, the inverse of that doesn't necessarily have to be the inverse of the antiderivative of that doesn't have to be the inverse of the original function, yeah. Okay, good, I mean, you gotta try something, right, yeah?
Take the natural log of both sides.
Okay, natural log of both sides. That's normally what people will do with this. I mean, you want to get rid of the e, right? Natural log.
Is that what you do?
Well, do you have something different?
Well, no, I have that. But
Okay.
I kind of have something weird. So, you know, there's like the, that doesn't solve with this. You know how subtraction.
I'm listening, but
What do you call that? So, we had that method that when you do a natural log, you can have, like, it can help, like, break down big polynomials.
yeah. Expanding and condensing expressions using logarithmic properties.
Yeah, I was thinking of, like, you distribute the ln, like, in between there, and then you, like, try to make that into a fraction.
Okay, pause. Is this kind of what you were doing, like take natural log on both sides? Okay, so this is the most natural step most students will try and do is do this, to take log so you can get rid of e. The problem with this is that when you go back and you look at properties of logs, the properties we have for logs are this. If you have natural log of, let's say, x times y, then you're allowed to split that up into the sum of two logs. So products inside of a single log turns into sum of two logs. That's a property of logs. Then if you have division of inside of a log, you can have subtraction. Does this all ring a bell from pre-cal a little bit? I mean, pre-cal college algebra? And then there's other properties. There's other properties. This one, which you used in Cal 1, is that if you have log of something to a power, the power can come out, right? That's a big property. We use that a lot in Cal 1, right? This. So we have these properties. Unfortunately, if we have log of x plus y, there is no thing that can turn into. Like that can't turn in, it can't turn into this, right? Because that's this. You can't split it, okay? So when you do natural log on both sides here, you have a difference. You can look at that as a minus here, doesn't matter. There's no property, and not to say that we've never found one, there just isn't a way to take a sum or a difference inside of a log and split that into two logs. You can't do it. Also, you can't just let the natural log kill these off individually. Like that, natural log will only kill off one e at a time. So if I do this, that's x. Natural log of e to the x, the natural log and the e are inverses. They kill each other off, you get x. That works, but not when you have two of them side by side. It doesn't work. Okay? So let me see. I've got 10 minutes. Let me see if I can do this in 10 minutes. You ready? So here's what I'm going to do instead. Instead of taking natural log, I told you I'm showing you this. Why? Why am I showing this to you? Why am I showing this to you? I said why.
We got one last suggestion.
Oh, you have one.
If we pull out e to the y,
What do you mean pull out an e to the y?
factor it kind of.
Yeah.
Factor on the right side. If you pull an e to the y out, what are you going to be left with? 1 minus e to the what though? Negative 2y. But then what are you going to do now?
You could take the natural log of that nonsense.
Okay, so if you did natural log on this side, natural log here, now you have a product. Okay, so I'm going to go ahead and go there. Natural log of e to the y would be the first one. Then I'd have, because it's multiplication, I have plus now another natural log, but it's of this thing, right? And unfortunately, again, even though this becomes y, this can't be broken down because you've got a minus inside, so you can't. So good try, good try. All All right, let me get to it because I need the time. I'm showing this to you because there's something algebraically here that most people would never think to do. And I want you to see it because I want you to think like, wow, you can actually go that far outside the box sometimes on things. All right, so here's what I'm going to do. I'm going to remind you that this e to the negative y, and don't feel bad that y'all didn't get it. If I gave you more time, maybe someone would get this, all right? 5 minutes is not enough time. All right, so that's the same thing, isn't it? So what I'm going to do now is I'm going to clear the fractions by multiplying everything by e to the y. That means e to the y here, e to the y here, e to the y here. Okay, so here's what I get. 2x times e to the y equals e to what? Yeah, I'm hitting this with e to the y again, so it's e to the 2y. And then the last term? Minus 1, right? Okay, well that I don't know if that helped at all, but I'm going to now move everything to one side of the equation. You're like, well, why are you doing that? Well, just stay tuned, all right? Stay tuned. It looks like a quadratic now. Okay, so look, do y'all see that? If I move that over, this term, and I stuck it in the middle on purpose, okay? If I rewrite this now like this, that's the same, this right here is the same as e to the y squared minus 2x times e to the y minus 1. Do y'all kind of see the quadratic here? It's like something squared, and then here's the same thing. Yeah?
Yeah.
But wait a minute, this should cause, this is the part that should make you go like, wait a minute, what? Because if you go back to our good old quadratics, this is what a quadratic looks like, right? That's a quadratic equation. And all quadratic equations can be solved using the quadratic formula, which is x is negative b plus or minus the square root b squared minus 4ac all over 2a, right? That's a quadratic formula. And we use that a lot, right, in our lives. But the thing about the quadratic formula was that a, b, and c are what? Constants, right? Numbers. Here, I have a quadratic. It looks like a quadratic where this right here, I'm going to use u instead of x. Let's just change this. u squared, right? u. So I kind of have like a u squared, right? Minus 2x u minus a number, right? So if you were to try and look at this as like a quadratic, what would a be? What would the number in front of this be? 1. So here a would be 1. What would b be? Negative 2x, which is not a constant, it's a variable, right? Can you do that? Yes, you can. Negative 2x. What's c? Negative 1. See, I have a quadratic here. Now what I'm going to do is I'm going to use this formula right here, okay? Use this formula right here, replacing a, b, and c with those a, b's, and c's. And one more thing, remember, u for us is not u. What is it? E to the y. So I have e to the y, how are we doing on time? E to the y equals negative, what's b for us? 2x. So I'm going to say negative, negative, right? Negative, negative, so it's positive 2x plus or minus the square root. Okay, b squared for us is, square that. 4x squared. Okay, minus, now 4 times a times c. 4 times a times c. Negative 4, but then it's subtracted, right? So plus 4. All over 2. Yeah? That's some weird shit, right? I mean, like you would never think you could use a quadratic formula that way. All right, e to the y equals, let's just clean this up. Do y'all see that these both have a 4? Pull the 4 out and then bring it out of the root. And it becomes a what outside the root? A 2, and then I have a 2 here, 2 here, and 2 here. So all the 2's go away. So I'm just left with x plus or minus square root, what's underneath the root? X squared plus 1, right? That's what e to the y is. Remember, we're trying to solve for y. Now, can you solve for y?
Yes.
Doing what? Taking the log on both sides. So now the left side becomes what? If I take the log on the left? Y equals natural log of the right side, x plus or minus the square root of x squared plus 1. Okay.
What do we do with the plus and minus?
Good. I'm about to point that out. So do you see in the answer here what I was trying to prove to you is that the inverse of the hyperbolic sine function was natural log of x plus that. We have what? Natural log of x plus or minus, don't we? Well, we're going to throw away the minus, and here's why. You can't have a negative in a natural log, right? It's undefined. How can you convince me? Think about that quantity right there, just underneath the root. Think about that quantity right there, x squared plus 1. That number, hold on, that number right there must be bigger than what? Bigger than or equal to what? 0, yes, but what other number? 1. The smallest that quantity could ever be is 1. Why? Because if that's 0, then that's 1, right? But if you take any other number and square it, you're going to be adding to that number. So what's underneath that radical right now, we know for sure, is that the smallest it could ever be is 1. And if it's any bigger than 1, what happens? If this number is any bigger than 1, we're taking, maybe I do it this way. Let's do it this way. Tell me which one is bigger, the red or the blue? What's bigger, the blue or the red? The blue is bigger than the red, right? Okay, but what is the red? That's just x, right? Okay, so what would happen if I took x and subtracted x? I would get what? I'd get 0, right? X minus x would be 0. But if the blue is bigger than the red, then x minus that would be a negative number, and therefore I can't do it. So I need to throw out the negative, or else it's undefined. If that makes sense, great. If it doesn't, your life's not over, okay?
Is that what the XER next to it's for?
No, this is just saying this works for all x, all real number x's. I would never test you on this, but isn't that, I mean, that's just kind of like, wow, like, that's a really weird way to go about solving an equation. Yeah.
You could do it for like a bonus question.
Yeah, we'll do it as a, prove the other ones. Homework-wise, I think you're good to try all the homework for this section off the schedule. There is that one problem with the catenary at the end. See how that goes. Yeah. All right, next class, we start antiderivatives. So we actually start getting into the Cal 2, all right?
Oh, so I noticed on the list of topics,
Yeah,
it says IBE. Is that integration by parts?
yes.
So the first exam will cover integration by parts.
I believe it does have it on there.
Because you also had integration by parts listed as that first topic.
So, yeah, so what I do is there'll be like basic integration by parts problems, like very simple ones. And then later, so on that first exam, there will be like, do you get the basic idea? You know, integration by parts, sometimes you have to do it multiple times. That won't be on the first exam, but it would appear later on the second. Yep, that's just the beginning of it. Yep.
One last question.
Yeah.
About how many problems do you use on exercising every bone in the body?
For the first exam, there's a lot more problems than, let's say, on like the second exam, because the second exam is more of just like finding antiderivatives, and some of them take a long time, so it varies. I will give you some sort of guide to tell you like about how many problems to expect, what things to focus on.
What's the smallest, like when you get down to like Taylor McLaurin kind of stuff, you already get down to like 10 problems?
Yeah, it's usually less than, I think the third exam is less than 10, or somewhere around 10. Yeah. Yeah, let me turn off my camera, because